Students, we're going to be working on our next section, which is doing the integral for the natural logarithm. Now, I think what might be a little misleading is that actually it's your answer that is a natural logarithm. So I wanted to start this by posing the question of why we have never integrated this type of problem. And so let's investigate that. If we did the power rule, then we would have x to the negative 1 plus 1 over, whoops, I just about gave it away. So let's try that again. Negative 1 plus 1 over negative 1 plus 1, and then plus c. Well, you see that this gives us x to the 0 over 0. And that's a problem because this would be 1 over 0, which is undefined. So I actually have never assigned to you a problem like this because the power rule does not apply. And instead, we have to have a new rule, and this is called the log rule for integration. So the integral, or the antiderivative of 1 over x dx, is equal to the natural log of the absolute value of x plus c. Now, what will normally happen is that it'll be 1 over and then some expression that we would need to use substitution for. So remember that all of those things that we did with integration there at the end, where we did substitution method, all of those things will apply. And then we also have the remaining 4 trig rules. Those do have integration rules, and they just all involve logarithms. So tangent is the negative natural log of the absolute value of the cosine of u plus c. For cotangent, the natural log of the absolute value of the sine of u plus c. Then we have the secant, you can see what that one is, and the cosecant, you can see what that one is. You might note that the ones that have natural log with a co in the answer, those are the negatives. Notice also that in all these cases, we have to have absolute value around the argument because the domain of natural logarithm is from 0 to infinity, not including the 0. So for these new trig rules, we will not do a great deal of practice with these. So whenever we take a quiz or some kind of assessment, which might involve these, I will provide you with a formula sheet. So you need to know how to use them, but I will not make you memorize them because we just are not going to get the volume of practice with these that we have gotten with the other trig functions. All right, so I'm going to move on to your first example. And as I stated in the opening, notice that this problem does not start off involving a logarithm. So I don't want you to think that we're integrating logarithms. We're integrating where your answer often will be a logarithm. So in this case, we have division that we cannot remove, so we're going to need to use a u. So u will equal the denominator, 3 minus x to the third, and then our derivative, which would be negative 3 x squared dx. So this doesn't look like anything new until we substitute. So I like to do a rewrite. So I'm going to have the 3 minus x to the third to the negative 1 power, and then my x squared dx. I feel like this is what you would naturally do with this. You would do a rewrite where you have this negative exponent. So I'm going to go ahead and do that. So we need a negative 3. Sorry about that. We need a negative 3. So we'll multiply by negative 1/3 to balance that out. And in doing that, we've created negative 1/3 times the integral of u to the negative 1. And then all of this is du. So until you get used to this, you may think to yourself, oh, I'll do the power rule. And so you can add 1 to the exponent, giving you a 0, and then you would have a 0 in the denominator, and hopefully that would trigger your memory that the power rule does not work on this. And so you would then hopefully remember that this is negative 1/3, and then this is the natural log of the absolute value of u, and then plus c. And then you just need to resubstitute. So negative 1/3, natural log of the absolute value, and then replace that with 3 minus x to the third in absolute value plus c. And so there you have an original problem, not involving logarithms, but when you integrate it, it is a logarithm. And again, if you do the derivative of this, you should get what we started with. So just very quickly, I think you can think about this. You'd have negative 1/3, and then you would have 1 over this expression. So there's where you see it in your denominator, times the derivative of this negative 3x squared, or the derivative, which would be negative 3x squared. You could get things to cancel, and you would end up with the original problem. So it does check, and that's why that definition works. All right, so we'll move on to your second one. And by the way, for the video, I spaced things out so that they're in a little bit different location than you'll find them on your notes page, but you should be able to follow along. All right, now this one does have a logarithm in it. So let's take a look at what we would do. Definitely we'll need to use a u. We have this multiplication. So I think that before I do the u, I am going to bring this 3 in front. So I'm going to do one rewrite. The integral of 1 over x times 3 natural log of x. That 3 just kind of gets in the way as I am going to set up the u. So my u is just going to be that natural log function, natural log of x. And then our derivative, du, would be 1 over x dx. Remember to have that. So if we try to rewrite this, I want to bring this natural log of x. Actually, I'm just going to leave it in the denominator. I'll show you that way. So 1 over the natural log of x, that's my 1 over u. And then this is times 1 over 3 times 1 over x dx. All I'm doing is just writing out these separated factors, which would really just be all of this multiplied together. So look at what my du is. I have this extra 1/3. So the 1/3 can just be moved to the outside of the integral. It's a constant, so we can leave it on the outside. So we have 1 over the natural log of x times 1 over x dx. And now I've got it in a form where I have the u and the du. So I continue to rewrite 1/3 integral 1 over u du. So I wanted to show you this written without a negative exponent. If you can catch it, rather than writing it with a negative exponent, which tends to make you think about doing the power rule, if you can catch it, if you're going to have a 1 over u, sometimes it's nice to just leave that, because your tendency is going to be to think, oh, that is a logarithm. So this would be now for your integration, we'll get 1/3 times the natural log of the absolute value of the u plus c. And then we can just substitute in. So our final answer would be 1/3 natural log absolute value of the natural log of x, and then plus c. All right, so there's your second example, and that's what your indefinite integration is going to look like. So on the back of your notes, I have 3 more problems I'd like for us to do with integration, doing a few different types of things with the integration. For the first one, number 3, I would like to have us solve this differential equation. So remember that when we have a differential equation to solve, we want to separate the variables. So we want to have the dr on one side, and then this fraction secant squared of t over the tangent of t plus 1 dt. And so we will integrate on both sides. So the right-hand side, the antiderivative of dr is r. On the that was the left-hand side. On the right-hand side, we have a quotient. We're going to need to use a u. So the u could equal, hopefully you're used to that being the denominator. That's usually a good choice. So the tangent of t plus 1, and its derivative, the derivative of tangent, is the secant squared of t, and the derivative of the 1 is just a 0. And remember, we have dt. Well, that's exactly what we have here. So you have the integral of 1 over the tangent of t plus 1 times secant squared of t dt. And so r equals the integral of 1 over u du. And so at this point, then, we have things set up to where we can do the antiderivative here. 1 over u would be the natural log of the absolute value of u, and then plus c. And we'll go ahead and substitute back in. And so the u, which was tangent of t plus 1, and then plus c. Now this problem has additional information. This would be the general solution. So we've found the general solution. Now we want to find the specific solution that goes through the ordered pair pi 4. So the answer that goes through the ordered pair of pi 4. So we'll substitute in the 4 for the r. And then this would be the natural log of the absolute value of the tangent of pi, and then plus 1, and we're solving for c. So remember to put that in there, plus c. Well, the tangent of pi is 0. So we'll have 0 plus 1. And so then that will simplify to the natural log of the absolute value of 1. Now, at that point, you don't need the absolute value symbol anymore because 1 is already a positive number. So it's the natural log of 1 plus c. Well, this is asking e to what power is 1, and that would be a 0. So this is 4 equals 0 plus c, and so your c is a 4. And so your final answer, the specific one that goes through the ordered pair pi 4 is going to be r equals the natural log of the absolute value of the tangent of t plus 1, close that absolute value, and then plus 4. So there you have your solution to this differential equation. So once again, notice we did not have a logarithm in the original problem, but your answer ended up with 1. Okay, you can also do the fundamental theorem of calculus with problems that end up having logarithms in them. For this one and for your next one, we will get decimal answers, and I'll have you round to the nearest thousandth. And so you would definitely be allowed to use a calculator for the decimal calculation, but I would want you to be able to show the work for the fundamental theorem of calculus. So, so we're integrating from 1 to 2, 1 minus the cosine of theta over theta minus the sine of theta d theta. So right away, we can see that we're going to need a u because we have this quotient. So we'll try out that denominator. So u would be theta minus the sine of theta, its derivative du. So since we're doing the derivative with respect to theta, this is our variable. So this will be a 1. And then the derivative of sine is cosine. So this will stay minus the cosine of theta, and then d theta. So as we look, that is exactly what we have. I'll do that rewrite. So we have the integral from 1 to 2 of 1 over theta minus the sine of theta times 1 minus the cosine of theta d theta. So exactly what we need for our u du. Remember that once you've changed this to the u, so this is 1 over u du, that you will need to adjust the limits of integration and not go back to this definition. So that means that I will be doing u of my bottom number 1, and it's going to look a little strange, but remember you'll get to use a calculator. So this is going to be 1 minus the sine of 1. So that's my lower limit of integration. And sorry about that. 1 doesn't look very good there. All right, and then we'll do the upper limit. So u of 2, and so that will be 2 minus the sine of 2. So that's my upper limit. And so now I'm ready to integrate. So the antiderivative of 1 over u would be the natural log of the absolute value of u. And then this is evaluated on my new limits of integration. So 1 minus the sine of 1 to 2 minus the sine of 2. And then I'll just plug those in. So that would be the natural log of the absolute value of 2 minus the sine of 2 minus the natural log of the absolute value of 1 minus the sine of 1. Make sure that your calculator is in radian mode, and you should find that this is approximately 1.929. So rounding to the nearest thousandth for that calculation. So there's an example using the fundamental theorem of calculus. And I have one last problem that I want to go over with you. I'm trying to hit the highlights of these last few units that we've been working with on integration. So one of the other main ideas was about the average value of a function. So remember that the formula for the average value of a function is the integral from a to b of f of x dx equals f of c, that would be your average value, times b minus a. Now, you could also have it solved for the average value, but this is actually your mean value theorem. So the a and the b are the 2 and the 4. So we will integrate from 2 to 4. Now, as I'm doing this, I'm going to distribute the 4. So this will give me 4x. I'm going to go ahead and write that over x squared plus, and then 4 times 1 gives me 4 over x squared dx. And I'm going to continue to write the formula equals f of c times 4 minus 2. Okay, so I can simplify this. So the integral from 2 to 4, this is going to give me 4 over x, which I could write as 4x to the negative 1, but I'm remembering that I can't integrate that. So I'm going to leave it 4 over x plus, and then this I will write with a negative exponent because I can do the power rule with this one. So 4x to the negative 2 dx, and then over here I can simplify 2 times f of c. So I don't really need to do any other rewriting. I could go ahead and do the integration. I do not need to use a u because I don't have either a product or a quotient that I can't deal with. So to integrate this, the integral of 4 over x will be 4 times the natural log of the absolute value of x plus, and then this I can use the power rule. So that's going to be 4x. I add 1 to the exponent, giving me negative 1 over negative 1, and then equals 2 times f of c. So notice how I'm maintaining that equation all the way through. I do want to remember that I need to evaluate this from 2 to 4. So now I can plug in the 4. So we'll do 4 times the natural log of, now I don't need to put absolute value around 4 because it's already positive. So 4 times the natural log of 4. I can simplify this a little bit and make this minus, and then this will be 4 over x. So that would end up being minus 4 over 4 if I plug in. So you may actually want to take a line and rewrite that. I might squeeze that in right here. 4 natural log absolute value of x minus 4 over x. That's what we're working with right here. So this would be 4 natural log of 4 minus 4 over 4, and then minus, okay, I'll use a parentheses. We're doing 4 times the natural log of 2. Again, I don't need absolute value for that. Minus 4 over 2. And then equals 2 f of c. Well, you can do some simplifying on this just to make it a little bit easier to type in. So this will be 4 natural log of 4 minus 1 minus 4 natural log of 2 plus a 2. And a little bit more simplifying. You've got some like terms that you can combine together. So we could also go ahead and divide both sides by 2 before we type it into the calculator. So the negative 2 and the 1 can be combined. You've got 4 natural log of 4 minus 4 natural log of 2, and then plus 1. All of that is over 2, and that's going to be the f of c. So plugging that into your calculator, and again, giving me 3 decimal places, the average value is 1.886. And again, this is the average value of the function. So I want to go back and make sure you realize this line right here, this was just to clarify this, and you may have wanted to do an extra line where you were getting ready to substitute it. All right, so those are your examples for today's lesson. We're just going to do one lesson on integration, so that one lesson is going to have several different pieces to it, and I tried to give you an overview of what those pieces would be. So this will be our last lesson with new types of either derivative or integration on it. We're going to do one other bridge lesson next week and then prepare for your quiz. Good luck on your homework.